Hello everyone. In this lecture, I'm going to give you a method to find a general formulation for finite difference approximation. So we were gonna find a general method for any order and any points that we want to find. We can do this and use this method, and this comes with the help of two things. First is the Taylor expansion, and the second one is the consistency requirements that we had for these type of finite differences. Okay, so in this lecture, I'm gonna just introduce the method, and then the next lecture we're gonna solve some examples of this, and also an example of truncation error and calculation. So this lecture would be mostly theory, and then the next lecture would be examples. Okay, so let's get started. General formulation for finite difference approximations, or I'm going to show it with FDAs. Okay. So all FDAs are of the form dmu over dxm to power m evaluated at x star can be approximated as sigma j equals to 1 to n of gamma j uj, where j corresponds to grid points or nodes. Sometimes we call it nodes or grid cells. So depending on the literature, we might say different names for this. So quick example. These we can approximate, for example, the first order one, du over dx at point xi can be written as ui plus 1 minus ui over delta xi, which can be written as minus 1 over delta xi times ui plus 1 over delta xi times ui plus 1, right? Which equals to, based on this formula, equals to sigma j equals to 1 to n of gamma j uj, where gamma j equals to minus 1 over delta xi, and this one is gamma I1, right? So gamma I is 1 minus 1 over delta xi, and gamma I plus 1 equals to 1 over delta xi and other gamma j's are 0, right? So based on this is gamma I, this is gamma I plus 1, and I can write it this way, right? So this is so this kind of shows the generality of this formula. We can write all the finite difference approximations as a sum of a coefficient gamma j times the value of the point at of u at point j, where j corresponds to a grid point or a node, right? So this is a kind of a very general way of writing finite difference approximations. And now the question becomes how to choose gamma j set. How to choose this set. How can we choose this set? Okay. So now we want to address this question, how we can find and construct gamma j's that correspond to this. Okay. Okay. So suppose only p of the endpoints have non-zero values of gamma j. Okay, so then I can write this as dmu over dx to power m evaluated at x star. I can write it as gamma p1 u p1 0.1 plus gamma 0.1 plus 1 u 0.1 plus 1, and this list goes on and on until gamma p1 plus p minus 1, right? So this is gonna be the pth point. Okay, so it's gonna be u p1 plus p minus 1. Okay, so we have total of p points in this approximation. Okay, and I'm gonna write this as P2 for simplicity. And so I can write the sum as j equals to P1 up to P2. Okay, so instead of 1 to n, I'm gonna write from 0.1 to 0.2 of gamma j uj. Okay, so this is the first step. Okay, so now I want to find these gamma j's. How can I find these gamma j's? Okay, so this is the question that we have, and we want to answer it here. So for this, I'm gonna use a consistency requirement. So I'm gonna use consistency requirement that we talked about in finite difference schemes. Okay, so the consistency requirement says that, for example, if this is the finite difference approximation, j equals to p1 to p2 of gamma j uj, then the error of the approximation, we can write it as dm over dmu over dxm at x star plus the order, right? So the order of this approximation, I can show it as delta x to the power r So the consistency requirement says that R should be greater than 0, right? What this means? This means that because this is your error, right? So this means that your error as delta x goes to 0 of your truncation error should be 0, right? So this was our consistency condition. And so this is only satisfied only if R is greater than 0. Okay. So what I'm going to do next is substitute Taylor series for each uj about x equals to x star. Okay. So I can write sigma j equals to p1 to p2 of gamma j uj as, I can just expand the Taylor series here and write it as sigma j equals to p1 to p2 of gamma j. So I'm gonna just expand the Taylor series here. So it's gonna be for each for uj, I'm just gonna write as u star plus du over dx evaluated at x star times xj minus x star, the first term. Then we have the second term, which is going to be d square u over dx square evaluated at x star, xj minus x star to power 2 over 2 factorial plus, so these goes on and on until dm u over dx to the power m x star xj xj minus x star over m factorial to power m, and this sum goes on and on. Okay. So this equals to I can just rearrange the terms and kind of open these sums, and what I'm going to get is sigma j equals to p1 to p2 of gamma j multiplied by u star, okay, plus sigma, the second term, j equals to 1 p1 to p2 of gamma j x minus xj minus x star multiplied by du over dx at x star. Okay. Then the third term is going to be sigma j equals to p1 to p2 of gamma j xj minus x star square over 2 factorial d square u over dx square evaluated at x star. And this goes on and on until sigma gamma j plus sigma gamma j xj minus x star to power m over m factorial multiplied by dm u over dx m evaluated at x star plus other terms, right? So this is how this can be written. Just opening the series, okay? So now I want to kind of separate the coefficients. So if you see, let's notice. So if you note, you see that U star is kind of common in all of these, right? In all of these, for example, gamma j U stars, right? So I can just take U star out of the sum, right? I can just factor U star out, and what I'm gonna get is this. So I can just write it this way. Let me write it down. So I can just factor out this here, okay? And the same thing for du over dx x star. I can just factor that out because the other terms are gonna be just multiplied by this. So I can just first do the sum and then multiply the whole sum by this du over dx star. The same thing for d square u over dx square. I can just factor out this d square over u over dx x square, and then first calculate this sum and then multiply that by this d square u over dx square. Okay, and finally the same thing here. Yes. So now I'm gonna name this. So I'm gonna name this one as f naught. This one I'm gonna name it as f1. These coefficients, and this one I'm gonna name it as f2. And this one I'm gonna name it as fm. Okay. So let's see. So this means I can write this sum as f0 u star plus f1 du over dx at x star plus f2 d square u over dx square at x star plus fm dm u over dx to power m x star, and this goes on, and this equals to what? This equals to this term, right? This is the sum on the left hand side that we expanded, and this equals to the right hand side of this equation, which is gonna be dm u over dx to power m evaluated at x star plus order of delta x to power r, where r is greater than 0 because of the consistency requirement here. Okay, so this comes from here, and this is gonna be the equality that holds, okay?